Alright kids, so here we are. I'm going to talk about redox reactions. Now, this is it's a longish one, so what I don't want you to do is I don't want you to be like Harley Quinn over here and choking out. I want you to hang in there and we'll see what we can get through. Okay, so the point today is you want to be able to, we're going to introduce electrochemistry, which is where we talk about, the generation of electrical charge or electrical change, and how that's caused by or interacts with chemical changes, basically. You want to be able to simply understand what a redox what a redox reaction is. So that's the concepts of oxidation and reduction and the different types of redox reactions. You want to also be able to understand the difference between, understand how reactivity of a metal affects displacement of metals in particular types of redox reactions. And you want to grasp the made up but useful concept of oxidation state. In other words, it's not an empirical thing, it's something we apply to reactions to help them make sense. Alright, so simply, sort of, and this is your 4.1, 4.2, so displacement and oxidation reduction. Okay, so we are going to go through this fairly quickly. Now, an oxidation reduction reaction, that's when electrons move from one species to another. Species is any of the different components within a reaction, okay? So any of the thing which is on the product side, reactant side, whether it be an element, ion, or molecule, they can be called species, okay? And it's just part of the jargon you need to have. So they consist of two half equations. We put them together. One half equation is a reduction equation. The other one is an oxidation equation. We put them together. They're simultaneously occurring, and that's your redox equation. So reduction is gain of electrons. Oxidation is your loss of electrons, and this is why we have the acronym oil rig. Oxidation is loss, reduction is gain. And any species which causes reduction are called reductants, but they themselves are oxidized. And the converse is true. So if you cause oxidation, you're an oxidant, but you yourself is reduced. Now, reduction occurs at the cathode, oxidation occurs at the anode, and this gives us a nice little mnemonic: red cat, so reduction cathode, oxidation anode, and ox. So red cat and an ox. And that's a good way for us to remember when we start talking about galvanic cells, which we'll get to next lesson. So displacement reactions are redox equations that occur, or redox reactions that occur when a more reactive metal displaces a less reactive metal from its solution of ions. Okay, so if we have a solution of a less reactive metal salt, and we put a more reactive metal in it, the more reactive metal will form cations by losing electrons. They'll lose those electrons into the metal which is in the solution, and when it loses those electrons to that metal goes, well, I'm now a free element, I'm a complete free element, and will drop out of solution, so they become solid. So electrons are transferred because the less active metal has a greater tendency to accept electrons, and the more active metal, well, I should say, then the more active metals who become electron donors. So you've got an electron donor, which is the more active metal, and the less active metal is an electron acceptor. So displacement reactions, when we put these with what we've done experimentally to create the activity series, remember we did that in year 11, we can use this to predict which way they're going to go. So the further apart the metals, the more vigorous the reaction too, and that's actually quite interesting. So, example. Now this says magnesium, but it could say zinc. So if we just give this a little boom, and we put like a, now it says that's zinc. So if we place zinc in copper sulfate, the zinc displaces the copper ions in solution. Okay, therefore it's oxidized because it loses electrons. Okay, so the zinc loses electrons, and therefore oxidizes. The copper in solution, it gains the electrons, so it's reduced, and because it gains the electrons, it is no longer an ion, it's now a solid copper, and it forms down the bottom. We get this deposition, and eventually the zinc will disappear, and you get this big mass of copper down the bottom. And as one of our students decided, that's an effective way to replace our dwindling sources of copper. So, go to the future. As the zinc dissolves, the copper solidifies. The solution changes from copper sulfate to zinc sulfate, and that's why the color here fades. And that's really important. All right, so this is a good way for you to decide whether a half reaction is oxidation or reduction. Okay, now is there a loss of electrons? So are there free electrons on the reactant side? Okay, is there an increase in oxidation state? Well, we'll get to oxidation state in a minute. Is there a gain of oxygen? Okay, so if you add oxygen to something, that means oxidation has occurred. The reason is, by the way, oxygen has a valency of -2, so anything that reacts with it will give the oxygen 2 electrons to equalize, so it oxidizes. A loss of hydrogen, which has a valency of +1, so anything reacted with it, it heightens its number of electrons. It gets extra electrons. And here reduction is just the opposite. Okay. Now, types of oxidation reactions. Let's go through these one by one. You've got displacement. So magnesium plus silver nitrate. Now we have all these half equations. So sorry, that's your full equation there. We're going to ignore that for the moment. We'll ignore this one here. They've made the ion equation there. So magnesium plus silver ion and nitrate ions gives you magnesium ion plus nitrate ions plus silver as a solid. Here they've taken the spectator ion away. We will look at probably this one here. That makes the most sense, and these ones here. Okay, so it's simplified down. You should be able to get to this stage by now. All right, so here we go. We've got an oxidation here and a reduction. That's a displacement one. Super simple. An acid metal, so sulfuric acid plus zinc. We come down here, okay, the sulfate here is the spectator ion, so we don't need to worry about that. We've got the hydrogen plus the zinc metal. Now you've got the zinc ion, so that means it's lost electrons. And the hydrogen here has now gained electrons, okay, so it's reduced. So reduction is gain, oxidation is loss, okay, so we've got an oxidation reduction reaction. We've got metals and non-metals, okay, so the sodium here has gone across because the sodium has given 2 electrons to the, 1 electron, sorry, to the chlorine. It's now an oxidation, it is oxidized, and the chlorine has taken an electron from the sodium, so it has reduced. An alkali metal, that's the left-hand side, they're the ones that react in water. Okay, so we've got potassium plus water. Now, the potassium lost electrons, which has gone into the hydrogen gas. Okay, so that has reduced, oxidized, sorry. Whereas the water has gained electrons. You can see how the water has split into 2 because it's gained electrons. And this has caused it to reduce. Okay, so this leaves us with potassium hydroxide and hydrogen gas. By the way, the reason it explodes, if just in case you don't quite remember, is hydrogen gas, extremely flammable. This reaction here, extremely exothermic. So while it's releasing hydrogen gas, it heats up beyond hydrogen's ignition temperature and boom. Now, the metal combustion. Now, what do we say over there? What are we adding to it? We're adding an oxygen. Okay, and because we're adding oxygen to it, to the metal, that means it's reduced, because as the oxygen joins up here, so boom, there's no spectator ion here, so as the oxygen adds right there, it's going to take 2 of magnesium's electrons. That has now oxidized because it's lost, oxidized the magnesium. The oxygen itself has gained 2 electrons, so it has reduced. All right. Now, here we're going to have a quick look at the what's this called? The activity series. Basically, in metal displacement, the active metal displaces the less active metal. So if we place copper in zinc sulfate, nothing's going to happen because the copper is not as active as the zinc. But if we place zinc in it, the zinc will dissipate out and will dissolve in, and the copper will solidify. So only more reactive metal will displace a less reactive metal. We can use the metal reactivity series, and anything on the left, so anything here, can replace anything to its right. So sodium here can replace anything to that side, but not potassium. As we've just said. Now, you don't actually need to learn this table. On the back of every periodic table that you are given, you'll be given an E0 table. So that's an electronegativity table. You'll be given an E0 table. The higher the number, the more likely it is to oxidize. The more likely it is to lose its electrons, and therefore it will react with anything below that. Okay, so if it's got a high E number, it will oxidize anything, also it'll displace with anything below it. Alright, oxidation state. This is part 2 of the video, and we'll pump this out, and this should make a bit of sense. So the oxidation state is a number given to any atom or ion to indicate how many electrons it's lost or gained. It's not a real thing, but it's pretty useful in determining whether oxidation reductions occurred, and you'll see that in the second video, which is a few calculations. Now, we give them Roman numerals. Even though they're usually the same as valency, we want to avoid confusion with valency, so we give them Roman numerals. So if oxidation has a positive oxidation state, so that means like plus 2 or 1 or whatever, then it is oxidized. Reduction occurs if it has a negative oxidation state. Okay, so if it's gained electrons, it's got a negative oxidation state. If it loses electrons, it's got a positive oxidation state. These are the rules. Free elements, 0. They have a 0 oxidation state. Simple ions, it's the same as the valency. Polyatomic ions, it's the same as the valency, which is stated. However, we can use this to work out what the oxidation state of this sulfur is. Okay, so for example, it's sulfate has a -2. We know that oxygen, we're about to get down there in a second, we know that oxygen has a -2 valency. So sulfate is 4 times oxygen plus sulfur, gives us +2, that's 2, not 11. Sulfur, in this case, has, so that's 8, okay, minus that, so we put that on the other side. Sulfur has a +6. Alright, pretty straightforward. Molecular compounds are like free elements. It's got a 0, because it's stable, it's not reacting with anything. Oxygen, -2, except in peroxides, which have a -1. Hydrogen is +1, unless it is a metal hydride, in which case it becomes -1. Okay, so that's alright. And that's us. That was a long one. Good luck, and I'll see you in class.